Next,
350.
Okay, next Friday, Professor Park from the engineering school is going to do a talk. One or two students actually know him already. Anyway, next time actually, Shaw, you can send an announcement to the department. So this place is really too small, probably a larger one. Let's see, okay? Find your file.
Okay, I think last week permit you end this page, so I keep on going with the next. Okay, actually my topic is metric entropy. First, I will introduce how to control the remarkable complexity. We introduce a notation called growth function. The definition of the growth function is defined as we have a two set is a map from one set to another set, and for a hypothesis set H, remember the hypothesis set H is infinite. So we extend our idea from finite set into infinite set. So we introduce the growth function to control the Rademacher complexity. So the growth function is defined as the maximum of absolute value of this given function h, and x1 to xm is the sample size.
Hold on. What is absolute value? What's that?
Oh, it's a cardinality also.
Okay.
And x1 to xm is a sample, and from the capital X, and the hypothesis set is said to be polynomial growth of order nu larger than 0 if it has satisfies the growth function is bounded by m plus 1 to the power nu for m is larger than 1. M is the sample size. Okay. Why we introduce the growth function? Because we want to, our goal is to bound the Rademacher complexity. And in the next page, we can see the growth function is closely related to the basic dimension.
But so first, probably, you need to talk about the meaning of this growth function.
Okay.
Just get people familiar with it. Because
Okay.
we're going to use it all.
I think
You read the definition, but several things to emphasize here. or some intuition? Like why we're taking like cardinality max? Why is m plus 1?
Because we don't want to because the hypothesis set H is infinite. We don't want to it has the growth function goes to infinite. So actually we want to this is bounded by some.
Can you explain what 13 means? Given any m is what? Control.
M is the sample size.
Okay, to control, and then you take the maximum.
Yeah.
What does it mean?
To control that means given the sample size, given a sample,
Given an arbitrary
sample
size, yeah.
and we can find the maximum cardinality of this function, of this hypothesis set.
All x is actually in this big X. For students who have taken, who are taking actually Dr. Young's class, this is nothing. But there are some students not taking the class, so I hope you can give some intuition. And then when you talk about say the growth fund, they directly say, oh, that is the the idea. Can we explain it a little bit?
Maybe I think I didn't.
So given any m.
I gave an example is combined with the VC dimension and the growth function.
Right.
I think maybe that will be.
Well, I still want to explain this definition. Maximum, what does maximum mean? x1 to xm. You didn't explain it, you just read the definition.
This H is the hypothesis function, and the maximum of the cardinality of this series of this function. That means I think maybe like.
Well, now I realize maybe like so you want to give an example in some sense, right?
Yes.
So you have H, the capital H, that's your set.
Yes.
You have all the sets, and then you want to talk about some cardinality, the maximum.
Yes. And maybe I think.
It's not difficult to give an example.
Yes, I think.
Anybody who can help him?
Maybe I think like a real life. Maybe a real.
So the classify the points.
Maybe a real life.
Real line is what?
Oh, real line is and give interval.
Classifier.
Oh, excuse me.
You can make edge to some kind of classifier.
Oh, that. Oh.
On the dimension.
You want to help him? I don't think he knows what other person perceive.
Commonly seen example when explaining VC dimension.
Yeah, but later you can see later VC dimension make a better connection. But right now, seeing the definition can still say something, right? H is hypothesis set. The capital H. And the small h there means what?
It's the hypothesis.
Yeah, it's small h. It's one element. And then you bound what set?
You found
The cardinality of.
the cardinality of the sample.
You're just repeating yourself again. This doesn't mean anything. You have to show the intuition. Yeah, I know it's the cardinality of this. If you teach a class, you want to show students what the meaning is, right? What does this notation mean? Well, take the maximum. And then we limit its growth. And then you can see why it's called growth function. What if m is 1 or 2?
When you want to, that means just one or two sample size. No, just one or two
you have to use some examples or point to the right thing. You just keep saying sample size, sample size. What does it mean? Can you talk about this thing just like in the real world?
I think I haven't thought about this. I just have some.
I don't believe it. You definitely know it. But you can't really say the jargons. You can't really only talk, oh, this is the sample size, this is the cardinality. Yeah, everybody knows that. You can't even explain this growth function? Why are you taking the maximum?
Because we want to find the biggest cardinality.
Can you go one step further? Yeah, you are doing this. Why? I'm asking why. Somebody go there and help him. You guys should be able to do it because some students are taking the course. All right. You want to talk? Go ahead. Go ahead. Don't chat about it. Just go ahead. Give a formal introduction. And what's the meaning? What is the logic behind?
So you have a set of hypotheses. So some kind of like with different parameters, you can make different hypotheses, and this the maximum cardinality given some kind of sample size plane, like if in an intuitively way, the power of this H to differentiate these xi's.
There's a keyword, differentiate.
Yeah.
Yeah. That's actually much better than, but it's still not clear. It's much better than just saying sample size, maximums.
Classification.
See, I mean, it's still not explaining things very clearly, but it's much better than what you did. Because he's thinking about an example. He's thinking about how to, let others understand. Well, you have to let people understand you. But again, actually, it's not very clear. Can you elaborate on this? You said actually differentiation, classifier, but not that rigorous enough.
If like a simple example, here I to talk about like the H could be for some range it takes value 0, others take 1. Then given samples on this, you apply the H function, you can classify them into 0 and 1.
That's not very clear. Maybe, but I know he understood. That's good. So shall we want to give a try?
Maybe not in a very short of time. It's just what kind of out of right of my mind. Yeah.
Okay.
On top of my head.
I think I understood, but let's move on. You have to do it. I mean, you are the teacher here. Next slide.
Okay. This is a theorem about how we found the market complexity. This is very famous. It's called Massard lemma. And first begin with the S is the sample, and RS is the supreme of the square root of the sum of the G is because in this definition we have the function class is capital G. The capital G is the function class. The small g is in the function big G. So the RS has been defined as the supremum of the square root of summation of G squared over n. And actually I think...
What is n and m? Start from the beginning.
Well, I think this should not n, it should be m. Let's get some type error. Okay, this is simple. This should be m. And what does this mean? This means the radius of this.
Can you give an example of this small g?
The small g.
Well, these are not really just mathematical notations.
Yes, I know. I think it's
I mean, like growth function, this is like a very useful tool. I do understand why you didn't even have some basic ideas of it. It's not just like there's a theorem. You see, you can link these two. But why? Why in the growth function can be linked? I mean, I'm not talking about the mathematical details. I'm talking about the intuition of growth function. Then you can see why it's connected to the complexity. But right now, you need to introduce the notation. You introduce what the problem is. There's a big G, there's a small g. The small g can be what? I mean, big G can be what?
big T is
Basically, I'm asking you to explain this L2 radius of this function family. If you can give an example of this radius thing, it's also good. Well, you have to say something.
I think I'm giving an example. Of what's the big T and what's the small t is.
And what do you mean by L2 radius? What is the meaning there?
L2 is
I'm not asking you to explain the two there. I'm asking the radius thing.
the
Not really.
radius. So maybe in a plane is like a circle.
No,
It's,
not necessarily.
Because
It's
this
not
is
the furthest two.
well, no, you're just checking the word. You didn't even think about it. I mean, you have to make an example of G, and then you can understand this better. I'm not asking the English word radius. Do you know why it's called the L2 radius? Anybody who can help?
It's the largest L2 norm between the. It's like two samples from that. So,
Two samples. Really?
I mean, like from the furthest from the origin.
Right now it's from the origin. Do you understand? What if G is identity function? What if G like quadratic? I mean, you have to think about these things. What does it mean? Why is sum over? I mean, it's the average G squared. Take the square root. But the square root is to get back to the scale, right? It's not going to be distance, as Dori just mentioned. It could be like some distance to the origin. It's not. I mean, this is not really valid study. In fact, you have to show people here what's the idea. So, what is the role of this S?
you mean it's a big S?
Yeah.
No, S.
Now you can use your plain example. Okay, move on. Move on, talk about 15.
So the Rademacher complexity is bounded by RS and times the square root of 2 log 2 times the growth function and divided by n. And from this inequality we didn't see any. I think in my first sight I think this is not very familiar to me because I don't know what are these means, the whole stuff. The boundary is like what? And maybe from 16 I get some more intuition stuff. And if the G is uniformly bounded by B, and the growth function is bounded by has polynomial growth of order mu, and this inequalities become like this. It's very like this is very like our dimension D, and this is like log m, and divided by m is very like the what we have in Lasso maybe. I think this is pretty like that boundary.
Again, talk about this B nu m.
B is the upper bound for G class function.
What do you mean by it?
What do you mean by G is bounded by B?
Yeah.
In what sense?
And why is uniformly?
Uniformly, that means the
Where is this G is a family, right? Where do you have this G have? The estimate for the family?
let's see.
What with it? I can see it here.
I think I should use this to denote what means uniformly bounded.
You're not explaining. Two students ask you questions. You have to explain in details.
So
Well, I'm not asking you to copy some notation, just theorems. You have to talk about the meanings. That shows you are eligible for teaching this thing. I said you don't have to teach much, but you have to achieve some kind of understanding. You don't say anything about it. I mean, the meaning, the underlying, like what is really reasonable here.
actually, when I prepare for this, I just focus more on how to get some example to illustrate.
Okay, that's fine. That's fine. Okay, later we're gonna see more examples. But right now, what is the message of this growth function and the theorem? What should we keep in mind? Later we're gonna use it, right?
Yes.
So what are the main points?
I think the main point is that the G is uniformly bounded by B is pretty much like it goes back to this. It means this superior is bounded by some stuff. I think that's why I was getting to this B. What does this mean?
I think they were asking you to explain why. I mean, what do you mean by G is uniformly bounded?
Yeah, like can you give a formula?
Just rigorous definition. G is uniformly bounded by B. You can do it. You can check the above thing. I mean, you wrote R of S, and you know you're gonna rewrite R of S as B, I mean as upper bound. So what is your definition here for this uniform boundedness? Well, let me ask you a question. Did you try to write down something on paper, or you just read the stuff? I feel like when you write down the notation, you're not really that familiar with it. You have to write, you have to just practice it. You can't say, oh, there's some theorem. I can check the paper, I can check the book to get it. You have to write it down. You have to prepare this thing without seeing any tutorial. Okay? What do you need for this uniform boundedness? Uniform boundedness still. Similarly, you're not really familiar with this thing at all. You should go through this several times. Maybe you can't really see all the picture, but still you can talk about what your understanding is. Okay, so G dot as a function should be bounded by G is a scalar. It's just it's not a multivariate thing. Okay, I mean xi can be multivariate, but G is just a mapping from say like some set to R. Little g. I'm talking about little g out there, right? So basically, you're saying actually there's little g dot. I mean, as a function, is uniformly bounded. I mean, for any g in the big G, and then you can simplify the R of s as B. That is what you said, in fact.
Yes.
So give me an example. G of this x, I mean, for any g and any x is uniformly bounded. In what case do you have such a uniform boundedness condition or assumption? Do you have any examples in mind?
Try sine and cosine for you.
Sine, cosine. Maybe yes, sine and cosine can be bounded by 1. The smooth line can be bounded by 1.
Okay.
And
So this
also-
limits the size. This G, this B, or this actually the uniform bound, limits the size of your like varying class. I mean functions in some sense. So you said B is like you said it's like dimension to you. It makes some sense. And what is that here?
M is simple size.
Yeah, sample size. I mean the sample size.
Yes. I said not B is like the dimension of something
New
is
is
like
that?
the
Oh, okay, okay.
dimension.
That probably is going to even be more, because you need to take a log. That's better actually. Okay, go back to the last slide. So can you say more about this growth function now? It's actually a very important class of tools. I believe in any textbook, this growth function is going to be introduced.
I think the growth
The
function.
growth function is in the next slide, log. Next slide. See, the growth function in 15 is a log of the 2 times. So now you simplify it to like nu times log m, right? There's a constant log 2, something like that. So nu is the power index. That's like the dimension 2.
Yes.
There's a log n. This depends on the sample size. So now we see the role of this growth function. Okay, go back to the last slide. Can you give more intuition now? We want to study its size as m grows. Why? What is the intuition of this growth function?
I think it's just related to the dimension and the sample size.
Dimension of the sample size.
No.
You think m is more important?
No, I think this is more important.
Very good. Nu is actually very more important.
So why nu is more important. So that's reason, and
Now